Okay, so today I will be working on the synthesis of nitrophenol using nitric acid and some pure phenol. It's an experiment I originally saw from ChemPlayer. Yes, I'm doing another ChemPlayer experiment just because I like their synths. And then once I'm done synthesizing the end product and separating it, I will then analyze it using a benchtop NMR and maybe some other methods. Haven't quite decided yet, but I hope you enjoy. Okay, this is very straightforward. So we're going to be using some concentrated nitric acid. This is 69 to 70%, which I'll dilute it a little bit. And then we're going to be using some phenol. And I happen to have a nice bottle of very highly pure phenol that I will be using for this reaction. So we'll be taking the phenol, putting it in an aqueous solution, adding to an addition funnel, and then we will have the nitric acid in a cooling bath, and we'll be slowly drop-wise adding the phenol solution into the nitric acid, which will then nitrate the phenol, and then we will separate the products after that. Alright, so we're getting ready to go here. Trying to get things set up, but let's get things going. Alright, we've got the nitric acid plus 80 mils of distilled water in the flask ready to go. Now we got to get the phenol solution into here.
Close enough. I think that right there is pretty good. Like it.
Alright, so according to my notes here, it says that the 40 grams of phenol is dissolved in 12 milliliters of water. That seems like a lot of phenol for a very small amount of water, but I'm going to stick to the procedure. Something in there. Rinse it out. Okay, let's try that again. Alright. Add that to the phenol. There's no way that's enough. If that all dissolves, I'll be amazed. Ooh, it's getting cold. I love that. It's so cool. Alright, for whatever reason, the phenol didn't exactly stay in solution. I don't know what's going on, but I mean, it's only, the only thing that's in there is distilled water and phenol, so I don't understand what's going on there. This is looking great. I've got everything ready to go. I've got the ice bath going. I'm going to be getting more ice here in just a second, and I'm going to go ahead and get the addition. The only reason that the temperature inside is not that low is just because my thermocouple is not quite reaching the liquid, but it's been there for a while. I know it's got to be cold, so I'm going to go ahead and get started. we're still chugging along here. I'm doing a pretty slow addition. Temperature hasn't really got up above this. I've been trying to keep the ice going, but I just don't have enough. It's gotten pretty dark in there. We're gonna keep it going. Hopefully I finish soon. Okay, so I just had to stop my addition just because the temperature was getting a little bit higher than I wanted it to be. So, golly, the solution's getting pretty dark. I'm trying to get some more ice, but I've got just a little ways to go. So, I'm gonna take a break for a bit and come back and finish this up. All right, temperature's back down. We're gonna start the addition again. Let's get back at it. Okay, complete addition is done. It's kind of funny, the fumes from the nitric had gone up the pressure equalizing line here and started to nitrate the phenol up in the top. So that was fun. But this took about an hour and it never really went above 24C. So now I'm just going to leave this for a bit, let it sit and finish up reacting, and I'll come back and put it in a separatory funnel. Okay, so I was going to pour this in the set funnel, but I'm just trying to demonstrate something here. So I don't even know if you can see it, but it's such a red liquid, but there's all this goo on the side there. And I am just not sure how I'm going to get that to transfer over. Alright, I don't think that stuff's going to go back in. Whatever, just going to pour it off. Set funnel is set up, ready to pour. Always remember your OOP speaker. Everybody needs to have their OOP speaker, just in case you don't close that. OOP speaker. Okay, so one of the things that is quite hard to see, I mean, it just looks like one big dark mass, but if you have your flashlight and you hit it just right, you can see that separation right there. So I'm going to try and track that down to here, and hopefully I do it correctly. Okay, so I've got the organic fraction separated here. Next step in the procedure says to add 100 mils of water, which I'm going to do. But I've also separated the aqueous phase that had a bunch of this stuck to the wall. I'm actually going to try and do something with this. I'm not sure what. I'm just curious what might be in there. So because I have the analytical capability, I think I'm going to try and take a look at it. But we'll see. Okay, this took ages to get back to. So I have the organic fraction here that has had 100 mils of water added to it, that I am now going to steam distill over and collect the distillate. And we have that at about 15C right now. So we're just going to collect that and see what we get. Alright, so it actually, I don't know why I didn't think of this, it actually started to plug that a bit. So I have emptied all the water out of the condenser, and I'm just going to be using that as an air condenser right now, so that then I can get all of that to eventually get washed down to there using the hot water from the distillation. So hopefully that'll work. Okay, so the steam washout didn't work. I actually had to shut everything down, tilt this vertically, and wash it with acetone. That's where it all went down into there, which is why you don't have anything precipitating out of solution. But it looks like we're back on track. So I'm going to keep doing this, and hopefully this will be the last time I have to shut it down. Alright, so as you can see, things have changed. I distilled it for as long as I could. I'm trying to get all the crud out of here, and I'm doing something that most people don't do for a very specific reason. And what I'm doing is I'm actually rinsing this out with acetone and taking all of that and putting it into this flask. Okay, so many of you might be wondering why I rinsed the distillation condenser and everything with acetone down into the receiving flask. You may be screaming at the sky going, oh no, now you've just diluted your product and you're going to have a hard time separating it. The reason that I've done that is because I have a piece of equipment that most hobby chemists don't have access to. And I'm not doing this to brag or anything. I'm just doing it to show that this is an alternate way to maximize your collection of your end product. So if I take the acetone and I rinse it all the way down into the flask, the next thing that I can do is I can attach that flask to a piece of equipment like this. This is a rotary evaporator. So I can take my sample in a flask. Let's, just for argument's sake, let's say it was like this here, right? So I can then take that flask and attach it to this system here, and it is rotated at this end here in a heated bath at about 50 C, and then I can use this oil-free chemically resistant vacuum pump to then distill over selected fraction. So I can set the temperature here to be constant, and then I can adjust exactly what I'm distilling using the vacuum and using these little valves here that I cobbled together. And what that'll allow me to do is to distill out the acetone and then leave behind the aqueous solution, and the end product here, which is going to be the nitrophenol, is going to be insoluble in the aqueous solution, so it should drop out or precipitate out a solution into here, and then I can vacuum filter and separate that product. But it also means that I don't leave behind all that extra nitrophenol in the column and in the adapters and all of that. I can wash it all the way down into the flask and maximize the amount that I collect. So it's a neat way of trying to collect everything as possible. Alright, so here's the fun part. We're set up. I'm getting ready to go here. I've got the flask with the aqueous solution, and there's a little tiny organic fraction down there. But I've got all that there. It's got the acetone, it's got the water, it's got the nitrophenol in there. And what I've done is I've set this thing up. So what I have is a cold finger. That's this whole thing here. It's really hard to see and it's hard to move with one hand. But this whole thing, right, filled with ice. And the way that this works is that cold finger, you can put enough ice in there, that's not a problem. But you can also put, like dry ice and acetone and get a very, very cold trap right there. It's really useful for whenever you're having to remove really volatile stuff, but for the most part, I have almost never used one of these that way. So I have that cold finger ready to go. I gotta put that green clamp back over that right there. And then what you gotta do is you come over here, you gotta make sure your bath temperature is correct. I'm running this at 50, some people run it at 60. It's really a matter of preference, or at least what the manual says. There's no need to go to 60 because then you start getting steam and everything, and I don't want to deal with that. In here is distilled water so that I don't get a bunch of minerals deposited in my heating bath. And then this is my rotation control. So this is gonna spin the sample, and that does two things. Number one, it increases the surface area that's exposed to the vacuum so you can get more material getting distilled out. And number two is, when you do vacuum distillation, if you don't have a stir bar or you don't have boiling chips, which is I don't have either in this, then you have to have something else that prevents bumping, which is rapid volatilization of gas that then can throw material over into here, and it screws everything up. So what you can do to get by that is using centripetal force. So the rotation causes the centripetal force that forces the material to the wall of the glass, and that actually prevents bumping. So it's kind of a lesser known way of getting around that issue. but it works really well, and this whole system can really rapidly distill volatile organic solvents, and it's the whole reason I have one of these things. These things are so nice to have if you can afford them. The problem is they're ridiculously expensive. I got mine off of eBay at a ridiculously low price. I got really lucky. I was patient for several years, and I finally got one. But actually, no, but I'm just happy to have it, and I'll try and show everybody exactly how this works. But for right now, here's the coolest part. Lower. Gotta press the button. Yeah, it's got a motor. It lowers the thing in the bath. I've never had one that does that. That's too cool. And then you just, set your RPM, hit the button, and there she goes. So I gotta put that clamp back on, and then I can turn on the vacuum pump. And then this is a bleed-in valve that I can use to slowly close the vacuum, which increases the vacuum pressure on the system, which then makes it to where you can pull over exactly what you want. So what you can do is you have a constant temperature here, which means you change the boiling point of what you're trying to pull off using the vacuum. So I can set it at a particular vacuum. As soon as I start to see acetone distill over here, then I stop changing that vacuum valve, and that keeps the boiling pressure constant so that I can only remove the acetone. And you can selectively remove solvents, which is another really awesome feature of this. So I'm gonna finish getting that set up, and then we'll see it run. Okay, so it's the next day. I let this sit in the fridge for a bit, and look at that. Look at that beauty. Just coated in it. I mean, wow. Little crystals floating everywhere. So what I'm gonna do is I'm gonna do a vacuum filtration. And I'm gonna see if I can extract as much as humanly possible. This is an acetone wash for cleaning the rotovap, and the reason I did that was because I actually accidentally vacuum, I guess, steam distilled some of the phenol, the nitrophenol, and it was on my cold finger here. It was in that little tube there, so I had to clean that all out. But I have a path forward, so I'm gonna set up the vacuum filter real quick and get this going. Okay, so real quick, this is my vacuum filter setup, and it's a little different than I've seen a lot of people use. The reason I have this is because a lot of the time I have to deal with very fine particulates, and I mean very, very small particles down in the 10 micron range, or sometimes even less. And to separate those, I actually have to use very special filters that are here. This is a filter membrane that is 0.22 micron, and it's a fluorinated material, so it's non-reactive. It's very resistant to chemicals. You can filter all kinds of things with it, but the thing that's nice is that you can catch very, very small particles, and you can filter quite a bit of material through. So that's why I have this set up. But the other thing that's nice is this thing right here unclips, and you can take this whole bit off, and then everything that you have on the filter frit you can just kind of scrape over to something. So it really helps to I guess effectively recover the maximum amount rather than trying to get down into a filter frit and scrape things off. It's just a nice thing to have. That's, you know. Truth. My product here, it's already teared from this way boat. Let's see what we get. Not bad. Take it. So I've got this beautiful yellow powder, and I want to analyze it using NMR, nuclear magnetic resonance spectroscopy. To do that, you have to get it in solution, but you can't just put it in any solvent because the solvents themselves, for the most part, are going to have a hydrogen proton. You don't want that. You want to look at only the hydrogens that are dealing with your sample. So to deal with that, you have to deal with something called a deuterated solvent, which I have. This is deuterated chloroform. And the reason that you use this is because the hydrogens that are in this compound are deuterium. Deuterium is an isotope of hydrogen, which means that it's going to have a different resonant frequency than what you would have for your normal hydrogen protons. So you won't see these with the way the instrument is calibrated, but you will see the hydrogens that are from this. That's the idea. So I got to make a solution of this, and then we'll go to the spectrometer and try and run the sample. Okay, quick aside, I forgot to mention this one thing. So I took this, put the solvent in there, and I'm not really supposed to do this, but I had to. And when I mixed everything, I noticed that it got very cloudy. So I added in some magnesium sulfate, and man, did it clump up. So there was a lot of water with my sample. Good thing to check when you're doing this, especially for proton NMR, is to make sure that you don't have water, because water has hydrogen, and hydrogen can interfere with your sample. So I added magnesium sulfate, put the sample in a syringe, and then passed it through a 0.2 micron PTFE cartridge filter. That then gave me this, which looks much better, minus the weird hair stuck to it. But yeah, that looks much better. That's what you want, is a nice clear solution ready for your analysis. All right, so we're all excited. We got our sample right over there, and we get to run it now, right? Not so quick. You got to calibrate your instruments, right? Or at least check and make sure that your calibration is good. So we come over here to the web browser. I'm actually running this through the IP address. That's the standard IP address for that instrument. And what I have done here is I've done a quick scan in the auto shim mode, which is that. If you click this little test box here, it will do one scan and it'll show you the spectrum that you get. And you calibrate this instrument using distilled water. So what you do is you take a little distilled water, which one of these is that. It's this one here, and you inject it in this little loop. It's about 40 microliters in this loop. Plug up either side. Then you come back over here, and I'm just going to show you. You come up over here and you hit start run, and I'm copying over this name, so okay. You'll see it do some stuff down there. And boom, there's one scan. And I got good signal to noise. That decay function there looks really good. So that tells me that the instrument is properly calibrated. I'm not gonna go through how to calibrate this thing just because it takes forever. But it is calibrated again with just some regular distilled water. So now that I know that's good, I can go to the one pulse function that's up in this corner here, and then we can set up running the sample. All right, It has been several minutes. Sample is in the spectrometer. It should be at the right temperature over there. Then I can come over here and I'm only going to do one scan to make sure that what I've done has worked. And you click start, and it's Nitrophenol, and I hope this works. Oof. May have made my sample a little bit dilute. That's what it is. So we'll see if I can make that better. Maybe I need to increase the concentration. Okay, so now the analysis has been run. I at least have the spectrum, so I can work with that now. Now I need to clean this out. So there's still sample in there. I need to take this syringe that has my organic solvent in it here, inject it here, do a few cycles of this to make sure I rinse that loop out completely. And then I'll do the same thing with a separate syringe that's up here using my distilled water so that I can be sure that I'm ready to go for the next sample. So I put water back in there, I can check my shim, and then I can make sure that the calibration is still good, and then go on to my next sample. Okay, so I just wanted to show this other thing. So I'm going to be comparing two different analyses. So you saw how the NMR was going to be run. So the setup, so running the sample, all that fun stuff. I'm not showing the data processing just because of reasons. But right now, I'm going to run an FTIR of this. So what I have is the NMR solution that had the deuterated solvent. Already done my background scan. You can see here, we're just constantly looking. There's a nice flat line here. There's no peaks or anything. So what I'm going to do is I'm going to take just a tiny bit of this, make sure it doesn't run out of my syringe or my pipette, over here on the ATR, and I'm just going to put a drop or two, and the rest of that is going to go back in there. Make sure I get it all out. I'll clean that up. But what I'm doing, so we're looking at that right there, as that starts to build up signal. So what's happening is that the solvent here is evaporating, and I can kind of take my hand and just waft a little bit there. So yes, there is a tiny amount of deuterated chloroform going into the air. It's not going to kill me, I'll be fine. But what it's doing, and this is a little trick you can do, is you can have something that's in solution and drop it on your ATR and let the solvent evaporate, and it will concentrate on the ATR crystal. And then you can get a good spectra of what your extract is. So it's a nice little trick that you can use in order to get a good FTIR with not that much material. So yeah, pretty cool. Okay, so it's been a few minutes now, and I've just been constantly scanning, and from what the previous spectra that you saw before, now you can see I'm starting to get all of this little detail here, all these extra peaks and everything. Another good indicator that what you're doing is actually showing the product that you want to see is if you come over here and you look at the ATR and you start to see it looks like it's starting to crystallize. If you just let that carry on for long enough, eventually you'll have just your product and you won't have any of your solvent left behind. So yeah. Okay, so I've worked up the data and I tried printing some stuff out, and it didn't actually go the way I planned, so I'm just going to show it on the computer. So starting here, we've got the phenol, and it looks about the way I would expect it to for a low field NMR. I can get some better signal and all that stuff. I can make some improvements on it, but you know, it's a decent enough spectra to tell me where I'm at. And then when we move over to the Nitrophenol, there is a clear difference, and I just kind of hit the idiot button as far as the assignments of all this stuff is concerned. I didn't waste my time on it. I was just wanted to show the spectra of anything else. Looks really good. That's really what I was hoping for to see here. And then just to be sure, I took the end product and compared it against my IR database, and that's pretty darn good right there. If I keep going down, you can see that it is a 96% match with 2 Nitrophenol, which is what I would hope for. So I'd say I did it. All right, and that just about wraps this one up. We've obviously done a lot with this. I think I've confirmed that I've made the end product I intended to make, so I'm happy with that. I still have all these other things. So this was the residual material from the distillation, so this is what was left in the pot. This is the aqueous phase that was separated after doing the nitration, and this is the aqueous phase that was also the water wash that came from cleaning all that off. And I'm still trying to figure out what I want to do with all these things, but if you liked it, please leave a like, leave a comment. If you want to see some other things, you have some suggestions you want to make, please make them, and I'll do what I can to try and keep keeping the content coming. So thanks for watching.